before we can look at patterns in the periodic table, we need to look a little bit at the noble gas form. The noble gas form isn't just a shorter form of the electron configuration. It shows the valence electrons. Valence electrons are the outermost electrons in an atom. They're the most likely to react or interact with other electrons. This can kind of make sense if you think about if you have your nucleus of your atom and you have layers of electrons for the different n levels. The electrons in the last n level are going to be the first ones that interact with anything in the environment. So these are going to be extremely important as we look at patterns. If we look at the valence electrons of all of the elements in the third period, you can see sodium has the electron configuration 3s1, so it has one dot in the Lewis symbol. We'll look a little bit at how we do Lewis symbols in a moment. Magnesium has 2 electrons in the valence electron shell. Aluminum has 1, 2, 3, so we have 3 dots here. Silicon has 4, 5, 6, 7, 8. We're starting to see a little bit of a pattern. These numbers are going up as we go across the periodic table. These patterns of valence electrons will provide us patterns to simplify reactions. So you're not going to have to try and figure out how each individual atom in the periodic table would interact with everything else. We can use patterns to help make it easier. They will help us to understand how things react and how things react in unexpected ways. Or things that seem unexpected at first but really do fit the pattern. Will also allow us to determine chemical structure and function. So first, I showed you the Lewis symbols. The Lewis symbols represent the valence electrons as dots placed on the sides of the element. So the way that we create our valence, our Lewis symbols from the valence electrons, is we count up the number of electrons that are in our valence, and we place them around the atom one at a time. So for example, if we look at carbon, it has 4 valence electrons. So I can write the symbol by writing the symbol carbon for carbon and placing 1 dot on each side. If I had more than 4, I would start pairing one at a time. But carbon only has 4 electrons, so I would stop here. So these are some examples of some Lewis symbols. We're looking instead at the second period of the periodic table. So notice lithium has 1 dot, beryllium is 2, boron 3, carbon here should have 4, got cut off. Nitrogen has 5, oxygen 6, 7, 8. You may also notice that if you look at the A numbers in your periodic table, this corresponds to group 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Notice that these numbers are exactly the same as the number of valence electrons. It's going to be a very important pattern throughout this course. So I'd like you to take a moment to practice the electron structures for each of these. For all of these, they're all in group 3A. So they're going to have this similar structure. Notice that with these dots, it's not as important which sides they're on as that we have 3 separate locations for them. Nitrogen, phosphorus, and acetylene, they all are in group 5A. So they're all going to have 5. Nitrogen, 2, 3, 4. I could also write it as 2, 3, 5. Or, so the double, this pair of electrons, it could be on any side. It just, you want to have one pair of electrons and 3 single electrons. This all helps to figure in to the patterns that we see in the periodic table. First, we're going to look at the atomic size pattern. Atomic size decreases as we go from left to right across the periodic table and increases as we go from top to bottom. If you think about it, it makes sense that the atomic size increases as we go down, because as we go down, we're getting more and more layers of electrons. The atomic size decreasing across tends to make a little less sense to folks. Sometimes I think it helps to look at the size is increasing this way. This has to do with the fact that electrons are negative and protons are positive, and how it ranges around the atom. The important part is that as we go across a row, the atoms actually get smaller. So lithium here is larger than fluorine as we go across, even though fluorine has more electrons. This will be important for looking at other patterns in a moment. If we look at ionization energy is the energy it takes to take away one electron. So if we look at sodium here, if we look at the orbital diagram of sodium, it has one electron in the 3s level, in the third level. So it's going to be very easy to take it away because we only have one electron out there. Also, if we look back at our size, sodium is kind of a bigger atom. So it's going to be easier to pull an electron away from a bigger atom, because in a larger atom, the electron is further away from the nucleus. So that negative charge is being pulled less by the positive charge in the nucleus. The ionization energy is low for metals and it's high for nonmetals. So the ionization energy pattern, the ionization energy decreases as we go down a column, and it increases as we go left to right. So this is the exact opposite of size. So as the atom gets larger, the ionization energy gets smaller. Metallic character is essentially about how easily something loses electrons. It's higher for metals, lower for nonmetals, kind of makes sense for something called metallic character, and it's higher down each group. So this pattern is the same as the pattern for size. So the larger an atom is, the more metallic character it has. This is just a summary table. You can find some of these in your textbook. If we look at a summary of the patterns, the metallic character and atomic size increase with the black arrows. So metallic character and atomic size both increase in those directions, and ionization energy increases in the opposite direction. So it's just taking a moment and practice. Then look at the references in your textbook to determine, can you rank each of these elements by size, ionization energy, and metallic character from lowest or smallest to highest, largest. As further practice, think about these questions. What is the largest main group element? What element has the highest ionization energy, not counting the noble gases? And what is the most metallic metal?